All right, let's jump in. So today what we're looking at is how to find the greatest common factor of a polynomial and how to use it to factor, right? To factor polynomials. So we begin with revisiting this concept of GCF, or greatest common factor, which is something that you've probably seen before. And just as a reminder, it's essentially just the greatest factor that can divide two or more numbers. So the two numbers that we're looking at here are 63 and 27. Now, for some of you, this might feel easy, right? To look at two numbers and see, okay, what's the largest number that can divide 63 and 27? And for some of us, it's a little bit maybe not as easy, right? So we have to list, one of the strategies is to list out the factors and then look to see which one is the largest one they have in common. So if you can identify it right away, great. If you have some trouble with that, then here's another approach. So we begin by listing the factors of 63, right? So I know that 63 could be the product of 1 times 63. So I could list out 1 is a potential factor and 63 is a potential factor. What else are potential factors that give us 63 as a product? Yeah, 3 and 21 actually, right? So 3, 21. What else? Yeah, 7 and 9, right? And I believe that's probably about it. So 1, 3, 7, 9, 21, 63, right? So these are the ways that we can list out all of the factors of 63. Then we can do the same thing for 27. What are some potential factors for 27? Obviously 1 and 27, right? And then 3 and 9. Right? And that's pretty much it, right? That wraps up our list of factors for 27. So then greatest common factor is looking to see, well, which factor do they have in common? Well, they have several in common, right? 1 in common, 3 in common, 9 in common. But greatest common factor is looking for which one is the largest one that they both have in common. And so what is that magic number going to be? Yeah, it's 9, right? So like I said, some of you are able to identify it right away. You're like, yep, it's 9. And then some of us, we have to list it out sometimes because we might not be as familiar with the factors of larger numbers. And that's okay, right? So this is a strategy that you can use whenever you need it. Okay, list out your factors, find the one that they both have in common. That is the biggest one. Okay, because 3 is a common factor, but not the greatest common factor. Okay. All right. So that's just revisiting the idea, and we'll have to apply that. The lowest common factor would be 1, but the lowest common factor is always 1, if you think about it, right? Because every number can be divided by 1. But we won't really focus on LCF in this situation. Okay, now what is factoring polynomials, right? And you probably have an intuitive idea of what factoring polynomials is. But essentially what it is to write a polynomial as a product of other smaller polynomials, right? So you think of a polynomial, how can I rewrite it in a way where I have multiple factors, right? Or smaller factors that if I were to multiply them, give me back that bigger polynomial, okay? And now when you factor a polynomial, what you do is you're writing that polynomial in an equivalent way, right? So a lot of times, especially when you take SAT or SBAC, you'll see the way that they describe what they want you to do. They'll say, find an equivalent expression. Find an equivalent expression. They won't say factor it. They just say find an equivalent expression. But that just means factor it, right? So that's why I put it in parentheses there, so that it's a link that when they ask for equivalent expressions, a lot of times what they're doing is asking you to factor a polynomial. Okay. So that's just a side note there, box number 2. Okay, let's go ahead and move on to the third box. So the reason why I bring this up, distributive property, is because looking for the greatest common factor is basically the opposite of the distributive property. If you think of what the distributive property does, is that it takes a factor and you multiply that into the other factor, right? So then this gives us 4x plus 20. But why is GCF the reverse, or why is it the opposite? Because with GCF, you're looking to see what is the greatest factor that can divide this expression, right? What number could divide both 4 and 20? Now, what is the largest one? And you would arrive that the GCF would be 4, right? So if we undid the GCF, I'm sorry, if we undid the distributive property, right? Distributive property gets us from 4 times x plus 5, but then GCF would take us back to 4 times x plus 5, right? So there's a connection between distributive property and factoring in that they're basically like a cycle, right? You distribute, and then if you want to undo it, right, it's the factoring process, okay? So let's take a look at it in action here in example 1. All right, so direction is to factor the polynomial using greatest common factor to write an equivalent expression, right? So you see how that language is coming in there. So notice how I have these two values. I have 21x minus 49, right? This is my my polynomial expression. So our job right now is to first begin with, well, what would be the greatest common factor between the two integers, right? 21 and 49. Yeah. So once again, if you needed to, you could list out the factors, right? Take your time. You have 1, 21. 21 could also be found by 3 times 7. And then you could do the same thing with 49 as well. You know, it'd be 1 times 49. And it could also be 7 times 7, right? So 49 has a factor of 7. So notice that that's the largest factor that they both share. So then 7 would be the greatest common factor. Now, what do we do with 7 if we want to factor this out? Well, the idea is that if 7 is the greatest common factor, then you're going to divide both of them by 7. Right? We divide both numbers by 7. So then the way that I'm going to write this is flipping, going from distributive property kind of backwards, right? So if 7 is what I'm dividing by, 7 is the factor that goes on the outside of the parentheses. Okay, and then once I simplify 21x over 7, that remains inside the parentheses. So 21x divided by 7 would give us 3x. And then negative 49 divided by 7 would give us negative 7. So you see, if I were to distribute the 7, I go back to 21x minus 49. If I divide by 7, 7 is the outside factor now. Right? 7 is the outside factor. So 7 times 3x minus 7, this would be the fully factored version of 21x minus 49. Okay. Any questions on example 1? Okay. Is this familiar? Have you guys done this or remember doing this in the past? Okay, good. All right. So it's just good review then. All right. Let's take a look at example 2. All right. So in example 1, we looked at one where it was only that the greatest common factor only included an integer, right? There will be times later on where it will be an integer and a variable, right? It's likely that a polynomial has multiple terms and there is a variable that is common to many of them. All right, so we'll see that as we move forward. All right, let's take a look at example 2. So in example 2, I have a trinomial, a little bit of a larger polynomial. And now I have 3 different terms to consider, right? I have 36. I have 15, and I have negative 9. Okay. So take your time, kind of think through, like, what could the largest factor be for 36, 15, and 9? Yeah, it's probably 3, right? Probably 3. So then if my GCF is 3, okay, I need to then divide every term by 3. Okay. And so as part of my rewriting process, my factoring process, 3, since that's the GCF, that term goes on the outside of the parentheses. Now, is there something else that all 3 terms have in common? We know that each value, each integer could be divided by 3, but is there anything else that they have in common? If you look, there isn't anything else, right? But almost, right? The first term has x, the second term has x, but the last one does not, right? So in order for it to be a common factor, all 3 terms must share it, right? But in this case, only the first 2 terms have x in common, so there's nothing else that we can factor out of all 3 terms. That makes sense? So then what we want to do now, try to clean this up as much as we can. 36 divided by 3, that ends up giving us 12x squared. 15x divided by 3 ends up being 5x. And then negative 9 divided by 3 ends up being negative 3. Okay? All right. And you know you have factored out the greatest common factor when the remaining factors, 12, 5, and 3, no longer have a factor in common besides 1. Right? The only thing that you could divide out of 12, 5, and 3 is 1, right? That's the only factor they have in common now. Okay? Right? Because if you think about 12, like you could divide 2 by 4 by 3, but 5 can't be divided by 3. So then there's nothing that all 3 numbers have in common. They don't have a common factor. So then this is how you know that 3 was the greatest common factor. Okay. All right. Any questions on 2? All right. Let's move on to example 3 now. Okay. So with this type of example, notice how now you have a 4x to the third minus 16x squared. You can identify that there between the 2 numbers 4 and 16, right? You might be able to see, okay, I think I see the greatest common factor there. What do you think it is? Yeah, it's 4, right? I see 4. So greatest common factor is 4. Now, what else do both terms have in common? They also have x in common, right? And now the question also becomes like, well, how many x's do they have in common? Because I have x to the third for one of them, and then I have x squared for the other, right? Yeah, they have x squared in common, right? X squared in common. So one of the ways that I like to teach it is, okay, you see that they both have x. What is the lowest power they both share? In this case, the lowest power they both share is x squared, right? It's power of 2, okay? Because I could divide x squared by x squared, and I could also divide x to the third by x squared, okay? So my greatest common factor is not only 4, but it's actually 4x squared, okay? So then when you identify your greatest common factor as x squared, that means you're going to divide both terms not just by 4, but by 4x squared as well. So when you rewrite it as an equivalent expression, 4x squared is your monomial term on the outside of the parentheses. What are you left with when you divide 4x to the third by 4x squared? Yeah, just x actually, because 4 divided by 4 becomes 1, right? So it's actually like 1x. But we don't need the 1, right? So it could just literally be x. All right, that's okay. And then if we look at the next term, 16x squared divided by 4x squared, what would be left there? Yeah, we'd be left with just minus 4. Okay? Because we see that x squared over x squared, that divides out to 1. So AKA cancels out. So we're just left with 16 over 4, which is 4. Okay, so we arrive at an equivalent expression here of 4x squared times x minus 4. Any questions so far? All right. Cool. All right, let's move on to example 4. All right, example 4, negative 9x to the 8th plus 36x to the 4th. Okay. All right. What do you think the GCF would be here? Okay. So first we look at negative 9 and 36, right? So between those two values, it looks like 9 would be the greatest common factor. 9 divides 9 and 9 divides 36. Now, one of the things that is a convention in math is that we don't want the leading term to be negative if we can help it. So if my leading term is a negative, I want to divide by a negative value, right? So negative 9 and positive 36, I actually want my greatest common factor to be negative 9. So I want to divide by negative 9 because if I divide by negative 9, that allows my leading coefficient now to be a positive. Okay. This is just convention when it comes to factoring. Okay. So what we're going to do is we're actually going to divide by negative 9. All right. So when the leading term, negative 9 does go into 36. It does. Negative 9 goes into 36 negative 4 times. Yeah. This is only when the leading term is negative. Okay. So we'll make a note after we've done the factoring. Okay. So what else did we say? We looked to see that, hey, they both have x in common, right? X to the 8th and x to the 4th. So because they both have the same variable in common, look for the lowest power that they share. So it would be 9x to what power can I factor out of both terms? Yeah, it'd be x to the 4th, right? That's the lowest power we see. All right, so we can then go ahead and divide both of these terms by negative 9x to the 4th, negative 9x to the 4th. So my factor, negative 9x to the 4th, would be on the outside. Inside of my parentheses, what is left over for that first term? Yeah, it's x to the 4th, right? Negative 9 over negative 9, that becomes 1. Don't need to write it. X to the 8th over x to the 4th. Remember that we just subtract the powers. So we end up with x to the 4th. Here, be aware of the sign change. We have a positive 36 divided by a negative 4. That ends up giving us negative 4. Okay, and then what happens with x to the 4th over x to the 4th? Yeah, they divide out, right? So they cancel out. We're just left with x to the 4th minus 4. Okay. Now, x to the 4th minus 4 is actually factorable again. We just haven't covered that, all right? But the emphasis on today is just to always begin by looking for a GCF. And this is something that I'm going to reiterate every time that we do factoring in every lesson, is that whenever you see a polynomial, you always try to factor out the greatest common factor first, right? It might be a binomial, it might be a special binomial, it might be a special trinomial, but no matter what, you first look to see what can I factor out first so that whatever's left in the parentheses is easier to factor once that greatest common factor has been pulled out. Okay, so I'm going to emphasize it over and over and over, and I'll always ask, what do we look for first? And the response should be, we look for GCF first, right? We're always going to try to identify a GCF because then it leaves us with expressions that are factorable. Right? We haven't looked at this one in particular, but eventually you'll see it. You'll be like, oh yeah, that's also factorable even further. Okay. So the note here is when the leading coefficient is negative, or when it's a negative integer, factor out a negative. Okay, and the reason why primarily is because when you factor out a negative out of the leading term, you're usually left with something inside your parentheses that can be factored even further. And it's a lot easier to factor out what's inside of the parentheses when this leading term is no longer negative. Okay, because if you would have only factored out 9, then you're left with negative x to the fourth plus 4. And it's a lot harder to identify ways to factor that than when the leading term is actually a positive. Okay, so that's why the convention is to factor out a negative with your GCF. And then you'll see examples of that in the future where it's like, oh, if I factor out the negative, oh, okay, now I see that this stuff is now factorable. It's a lot easier to factor because that negative is no longer there. Okay. All right. Any other questions on example 4? Okay, cool. Let's move on to 5. Okay, so I have 56xy minus 64y. All right, so I have a polynomial here with multiple variables. So first off, let's begin by identifying what could be the GCF between 56 and 64. Okay, 8. What do you guys think? Do you guys agree? Yeah, I think it's 8, right? Looks to be like that's the greatest common factor for the integers. Now, what else do both terms have in common? Yeah, they also share that variable y, right? Now, what is the lowest power? Well, notice how they both have y and y. So that's technically like y to the first and y to the first. So then the y that we can factor out is just going to be 8y, right? Just y to the first power. That's the lowest power that they both share. That's the y that we're going to be able to factor out. So we're going to divide the entire term by 8y. So 8y goes to the outside of my parentheses. 56 divided by 8 gives us 7. Y divided by y cancels. So then we're just left with 7x. 64 divided by 8 would be 8. Y divided by y would also cancel. So we would be left with this as our final expression. Any questions on number 5? Okay, cool. All right, let's take a look at 26. It's kind of the beefed up version of number 5. All right, so I've created a little bit of like a hint on the side. Notice how I've also listed out, right, or I want to find out what is the lowest power of x that they share, what's the lowest power of y that they share, right? Because you can see how both terms have x and they have y, right? But you only want to factor the lowest power that they both have in common, right? So if you look at 25 and 10, right, what do you identify as the greatest common factor that divides both of those values? Yeah, that's just 5, right? So between these two, it's just 5, right? That's the greatest common factor. What about the lowest power of x that they share? Right? It's x to the third and x to the fifth, so they share x to the third, right? They can both at the very least have x to the third. And then what about the y? There you go, right? The lowest power, y to the fifth, right? So they both terms have at least y to the fifth. Okay, so our greatest common factor is a combination of all three. It's going to be 5x to the third, y to the fifth, right? That is what both terms have in common. They can both be divided by 5, they can both be divided by x to the third, and they can both be divided by y to the fifth. So then we divide all of it by 5, x to the third, y to the fifth. Okay, and we're just going to go piece by piece. Okay, don't let this overwhelm you. We begin with, well, first I know 5x to the third, y to the fifth is my factor. That's my greatest common factor. Write it on the outside of the parentheses. 5 divided by 5, begin with that, right? Just your numbers. So that's just 5. Then focus on your x only, right? X to the third over x to the third. What do we know about these two? What's going to happen to them? Yeah, they cancel, right? X to the third over x to the third. Right? They divide out, they become 1. We say they cancel. What about y to the fifth over y to the fifth? Same thing, right? They also cancel, right? So it's just 5. It ends up just being 5. Minus, now we look on the other side. We have 10 divided by 5, so we focus on just those values. So it's just 2. X to the fifth over x to the third. X to the fifth divided by x to the third. We arrive with x squared. Good. And then the same thing here. We have y to the seventh over y to the fifth. What do we get? Yeah, we get y squared. Okay. So there it is, right? So you break it up into parts, right? Look for the common factor between the integers. Look for the lowest power of x. If they both share x, then we look for the lowest power. If they both share y, we look for the lowest power. And then that is what helps us build the GCF when there's multiple parts to it. Okay. Any questions there for number 6? All right, good, cool. All right, number 7 is just me kind of messing around here. You have 3 happy face to the 7th minus 27 happy face to the 5th. All right, so what's a GCF here? Yeah, so first, right, between the 3 and the 27, GCF is 3. What else do they both have in common? Yeah, happy face, right? Happy face, treat it like a variable, right? So happy face to what's the lowest power that they have in common? Right, it's to the 7th and to the 5th, so it's happy face to the 5th. There we go. So 3 times happy face to the 5th is my greatest common factor. Okay, so we're gonna divide by 3 happy face to the 5th all over 3 happy face to the 5th. Okay, so we end up with 3 happy face to the 5th as the factor on the outside of the parentheses. What would be the term inside the parentheses? What are we left with? Okay, we got a happy face squared. And then minus 9. There we go. Right, since I happy face to the 5th over happy face to the 5th, these terms cancel out. Okay. And again, when you see this problem later on, maybe like Monday, you'll notice there's something else that can be factored out of this. There's a way to factor even further. And so a lot of it begins with, if you can factor out a GCF, then it reveals a new polynomial that can be factored even further. Okay. I'm sure you might remember like difference of squares. That is one of those that usually gets revealed after you do a GCF factor. Okay. All right. And so then I'm gonna leave you with this one here. I want you to go ahead and try it out on your own, right? It looks like a monster, but it's actually not too bad if you break it up into parts. So go ahead and try it. Give you about 3 minutes or so, and then we'll come back together and work it out. All right, let's take a look at what you may have found. So we look for greatest common factor between the integers. That looks like that would be 2, right? So between 6, 2, and 4, largest factor that divides all of them is 2, right? They all share x, right? They all have x in common. So we have x squared, x, and x, right? So it looks like the lowest power of x that they all share is x to the first. The lowest power of y, it looks like we have y to the third, y squared, and then y squared again. So it looks like y squared would be that lowest common. And then we have z. They all have z as well. So z squared, and z, the lowest power there would be z to the first. So we can only factor out z. So then our GCF becomes all of them grouped together as a product. So it's 2xy squared z. That would be my GCF. So I'm going to go ahead and divide all terms by 2xy squared z. And also listed as the factor on the outside of the parentheses. Okay, so 6 divided by 2, that's 3. X squared over x, that's just x. Y to the third over y squared, that's y. Z over z, these cancel. Okay, so we're left with just 3xy as my first term. Second term, plus 2 over 2, that's just 1. X over x cancels. Y squared over y squared cancels. And then z squared over z, I'm left with just 1z. Okay, or z, all right, depending on how you wrote it. And then finally, -4 over 2, that's a -2. X over x cancels. Y squared over y squared cancels. Z over z cancels. Okay, so then our final term is just -2. Bring the parentheses a little closer. Okay, so this ends up being our final factored form here. All right, any questions on number 8? How did we do? Pretty good? Yeah. All right. And now our last one. Okay, this one is important to see as well. So take a look at number 9. Do you identify anything that could factor 13, 19, and 53? So 13 is prime. It can only be factored by 1 and 13. 19 is prime. It can only be factored by 1 and 19. So already right there, there's a problem because there's no two numbers that could actually divide 13 and 19. So there's no way that there's going to be a number that could factor all three. Okay. So you're kind of on the right track, Haley, right? It seems like the only factor they have in common is 1. Do they have any variables in common? No, right? So when the greatest common factor is 1, there's no point in factoring because if you divide everything by 1, you're going to be left with the same expression, right? So in this case, this is something that we call a prime polynomial, right? Or a prime polynomial because it cannot be factored any further. All right. So this is what we call a prime, kind of like a prime number. Right? Kind of like a prime number because prime numbers can't be factored any further besides dividing by 1 or dividing by the number itself. So we call it prime, right? This is when a polynomial has a GCF of 1, right? Where 1 is the only thing that divides all three terms, that's when we call it a prime polynomial. All right. And that's it.